Hello, welcome to the Short Span Steel Bridge Alliance's 2020 topic-based video series. In this series, we'll review basic concepts and ideas pertinent not only to engineers new to short span steel bridge design, but those looking for a refresher of fundamental concepts. In this video, we'll discuss suggested fabrication details for short span steel bridges. Our goals will be to provide engineers with an overview of simple, efficient, and economical fabrication practices for short span steel bridges, as well as to provide engineers with guidance on designing and detailing steel girders for these types of applications. This video is part of a two-part series on suggested fabrication practices. The first part will cover the overall framing system layout for a short span steel bridge application, whereas part two will discuss suggested fabrication practices for individual girders and elements. An excellent resource on this topic is the series of AASHTO NSBA collaboration documents made widely available for download, specifically G12.1, the Guidelines to Design for Constructability. You can find this document at the link shown. I should note that this video only covers recommendations relevant to short span I-girder bridge options and only projects up to 140 feet in span length with relatively simple geometry. Also, keep in mind it is always the responsibility of the engineer of record to ensure that all designs meet safety requirements as well as any applicable federal, state, or local standards. To begin our discussion, we'll begin by looking at the two primary girder options available when utilizing short span steel bridges. And those are rolled beams, which an example of that might be something like a W36 by 135, but really any of the rolled W shapes commonly available at steel mills or service centers, as well as plate girders. So a plate girder would be an I-shaped cross-section that's been fabricated from structural plate. Based on previous work that's been conducted by the Bridge Technology Center of the Short Span Steel Bridge Alliance, we found that rolled beams prove to be economical for spans between 40 feet and 100 feet, whereas plate girders prove to be economical for spans between 60 feet and 140 feet. Keep in mind these are general recommendations, and there are ranges, for example, between 60 feet and 100 feet, where there are two options that prove to be economical. It's always a good idea to consult a fabricator on the best solution for a given project. When laying out your project and choosing the number of girders in your given cross-section, generally what you'll find is that the fewest number of girder lines will result in the most efficient and economical system for your project. Here on the right, we have a plot that shows the average structural steel weight for a given project as a function of span length. The plot has been normalized to plot the average steel weight per square footage of deck area for a given bridge. And what you find is that as the girder spacing increases, the actual total steel weight for a given project decreases. The idea is that while the individual girders themselves may be heavier, because you're spacing the girders farther apart, you need fewer of them. And so overall, you'll find that wider girder spacing tends to lead to a most efficient system. Now keep in mind this is a general recommendation. Your individual project may require you to space girders closer together due to specific project constraints such as vertical clearance issues or hydraulic opening requirements. When laying out the cross-section, we've found that an efficient cross-section utilizes an overhang width that's roughly about 30% of the girder spacing. Here on the upper right, I have a schematic showing a typical bridge cross-section. This is utilizing a 4-girder option. You can see that the girders have an even spacing, and there are 2 deck overhang widths at the end. What you see here on the bottom are 2 bending moment diagrams, assuming that the deck is your flexural element and each of the beams serve as simple supports. And what we have are 2 cross sections that utilize different overhang widths. The upper one utilizes an overhang width of 15% of the girder spacing, whereas the lower assumes a 30% of the girder spacing. Both of these models utilize the same out-to-out width as well as the same loads for a typical short span steel bridge. What you find is that by utilizing an overhang of 30%, you generate a more equal distribution of loads across the cross-section. For example, if we investigate the 15% overhang scenario, we find that the positive bending moment in the deck regions is very unbalanced. We have high moments in these end segments, whereas low moments are present in the central segment. Also, the negative moment across the girders is much different. We have a lower negative moment here at the exterior girders versus the interior girders. It's much higher. Utilizing a 30% girder spacing, we find a much more even distribution of bending moments, not just across the girders, but across the deck as well. Keep in mind that this is just a general recommendation. The loads across your given cross-section will arguably be different than the ones that were assumed for this analysis. But again, this is just general guidance on laying out a cross-section. Keep in mind to always reference your federal, state, and local standards for more guidance on this issue. In terms of field splices, so this is when your girder would be brought out in individual pieces and then spliced together. Field splices for plate girder solutions really shouldn't be necessary until you reach spans of around 100 feet. Now this might change for projects with significant transportation issues, but by and large, for most general projects, you shouldn't need to splice at spans up to 100 feet. If a field splice is necessary for bridges in the short span range, you shouldn't need more than one, and at the very most, two. No, you really shouldn't need any more than that. Also, try and locate the field splice at the same place as a flange transition. So this is where you would change the size of the flange across the span of a given girder. In terms of actually designing the splice itself, we would highly recommend NSBA Splice. It's a free resource that greatly simplifies the design process and can be found on the National Steel Bridge Alliance's website. Your project will definitely need the inclusion of crossframes or diaphragms. Crossframes or diaphragms are necessary to brace the girder during placement of the concrete deck. A few notes when laying out crossframes and diaphragms. Diaphragm spacing is usually kept between 20 feet and 30 feet. Previous editions of the specification specified a maximum limit of 25 feet. While that limit is no longer present in the specification, you will find many engineers still use that as good guidance on laying out crossframes, and it is still a reasonable value for an unbraced length for a given girder. For low skews, and by low skews we mean skews under 20 degrees, diaphragm should be oriented parallel to the skew, whereas for high skews over 20 degrees, diaphragm should be oriented normal to the girder or perpendicular to the girder line. Now, in most short span applications, the question becomes, should we use a crossframe or should we use a diaphragm? A channel or bent plate diaphragm offers significant economy in the short span range. While the individual element may be heavier than a X or K-shaped crossframe, it is much easier to fabricate and much easier to erect on site and should definitely be considered for a short span application. There's been a lot of details presented today, and it might be difficult as an engineer to wonder where to start with detailing a given short span steel bridge project, and arguably eSpan 140 is the best starting point for beginning a short span steel bridge project. Based on very simple input, eSpan 140 provides a preliminary design for a short span steel bridge, including rolled beam and plate girder details, as well as details for other systems such as buried soil steel structures and manufacturer prefabricated solutions. eSpan 140 is a great resource to begin your project and to provide a preliminary design. It is free and easy to use. You can find eSpan at the link shown. We highly recommend that you all check this resource out. That concludes this topic-based video. We appreciate your attention, and we will see you in our next video. Thank you very much.